Missile defense was built for dozens. Modern warfare sends hundreds. Patriot PAC-3, THAAD, Aegis ballistic missile defense, and Iron Dome were each shaped by the threat landscape of their era. In the late 1990s and the early 2000s, designers faced adversaries fielding limited numbers of ballistic and cruise missiles, not the mass barrages seen today. Their solutions reflected this reality. Each system was assigned a specific role within a layered defense, with deliberate overlap and redundancy built in to maximize the odds of intercepting an incoming missile before it could reach its target. Patriot PAC-3 was engineered for terminal phase interception, using hit-to-kill technology and a sophisticated radar to track and engage a small number of ballistic or cruise missiles at high altitude. Batteries typically field up to 16 interceptors per launcher, optimized for a handful of threats at a time. THAAD pushed coverage higher, targeting medium-range ballistic missiles near the edge of space. Each launcher carries 8 to 12 interceptors, and its X-band radar sorts warheads from decoys, but always under the assumption that salvos would remain limited. Aegis, deployed at sea, was designed for exo-atmospheric intercepts using Standard Missile 3, with vertical launch cells arranged for rapid response to strategic threats. Iron Dome, tailored for Israel, counters short-range rockets and artillery, its Tamir interceptors and radar prioritizing the most dangerous tracks rather than overwhelming barrages. None of these systems guarantees a single-shot kill. The probability of kill has always been less than 1. To raise the odds, doctrine calls for firing 2 or more interceptors at each incoming missile, a calculated response to the realities of guidance errors and electronic countermeasures. Redundancy, not perfection, was the guiding logic, setting the foundation for the arithmetic of capacity that follows. Missile defense systems like Patriot PAC-3, THAAD, Aegis ballistic missile defense, and Iron Dome all face a hard ceiling, magazine depth. This is the physical and operational limit on how many interceptors a battery can launch before it must reload or resupply. The math is straightforward, but unforgiving. A typical Patriot battery fields up to 16 interceptors per launcher, with 4 launchers yielding 64 ready missiles. Doctrine calls for 2 interceptors per incoming threat, sometimes more when the probability of kill drops because of clutter or decoys. That means a single battery can reliably defend against only 32 targets before running empty. This is a hard limit. Radar and fire control channels impose their own ceilings. The ANMPQ-65 radar on a Patriot battery can track 100 to 200 objects at once, but the system can only engage around 20 threats per minute. Under real-world conditions, such as a mixed barrage of 60 cruise missiles and drones, those channels fill up fast. The saturation index, or SI, measures the ratio of simultaneous threats to available interceptors. When SI exceeds 1, meaning more targets than interceptors, some threats will inevitably leak through. In Ukraine, for example, Russian drone and missile waves have repeatedly pushed SY well above 1, forcing defenders to prioritize and to accept gaps in coverage. Even the most advanced radars and launchers cannot escape these arithmetic limits. If 60 incoming targets arrive within a few minutes and a battery has 32 interceptors loaded, the best-case scenario is partial coverage, not a perfect shield. Fire control engineers have modeled this outcome for decades. High-volume attacks compress the engagement timeline, overwhelm tracking and launch rates, and quickly deplete magazines. The magazine depth problem is not a flaw in engineering. It is a structural constraint that defines the outer edge of what any single battery can achieve under saturation. Hypersonic glide vehicles have redefined the timeline of air defense. Unlike traditional ballistic missiles, these weapons maneuver at speeds above Mach 5, shifting unpredictably as they close on their targets. For operators managing systems like Patriot PAC-3 or the THAAD system, the engagement window that once stretched for several minutes now collapses to as little as 90 seconds, or even less. The process from initial detection to launch authorization is compressed, leaving little room for error or delay. Each second lost to radar refresh rates or command chain hesitation narrows the chance of a successful intercept. They do not follow the predictable arcs that legacy missile defense systems were built to counter. Instead, they exploit gaps in radar coverage and force defenders to predict a moving target that can change course mid-flight. The decision loop, detect, classify, assign, engage, must now operate at a pace that strains both technology and human judgment. Operators face a scenario where the margin for action is measured not in minutes, but in fleeting seconds. This compression of time is not just a technical challenge, it is a structural one, reshaping every aspect of how air defense is planned and executed. The economics of missile defense are defined by a stubborn imbalance. On one side, a single offensive drone, like the Shahed 136, can be produced for $20,000 to $50,000. On the other side, interceptors such as those used by the Patriot PAC-3 or the THAAD system often cost between $150,000 and $500,000 per shot, with some variants reaching several $1 million. This cost ladder is not an accident of procurement or a temporary supply issue. It is a built-in feature of modern missile defense systems, where advanced guidance, rare materials, and rigorous testing drive up expenses for every interceptor loaded into a launcher. Meanwhile, the attacker's tools, drones, low-cost cruise missiles, even decoys, are getting cheaper and easier to mass produce. Every time a $30,000 drone triggers a $500,000 interceptor launch, the imbalance grows. Defense economists have a simple way to put it. It costs less to overwhelm a defense than to build one. This arithmetic plays out in every theater where layered air defense faces saturation, draining budgets and inventories at a pace that no incremental engineering can reverse. The challenge is not just technical, but financial, a structural gap between what it costs to attack and what it costs to defend. Ukrainian air defense crews face relentless waves of Shahed drones and Caliber missiles, often exhausting up to 80% of their interceptor stocks in just 4 nights of heavy attacks. Emergency airlifts struggle to keep pace, with resupply cycles stretching over 2 days and leaving critical gaps. Each shipment relies on a global supply chain already strained by scarce components and slow production. In the Red Sea, U.S. Navy destroyers equipped with Aegis systems burn through missile magazines as they intercept not only real threats, but also decoys and low-flying drones. Up to 15% of SM-3 launches have targeted false tracks, draining inventories before main attacks even begin. Reloading these ships' vertical launch cells means returning to port, a process that can take weeks. Across the Middle East, Iron Dome batteries have engaged barrages mixing rockets, drones, and decoys. In one 30-minute clash, operators fired at over 150 rockets and 30 unmanned aerial vehicles, with a 22% interceptor waste rate from decoy saturation. Logistics planners scramble to reallocate to mere interceptors, sometimes delaying readiness elsewhere by days. United States missile defense systems face a hard arithmetic when it comes to inventory and production. Each year, the United States produces around 500 to 650 Patriot PAC-3 interceptors, despite growing demand from active theaters and allied commitments. For the THAAD system, output is even lower. Roughly 100 interceptors roll off the line annually. These numbers are not the result of oversight or underinvestment. They reflect the complexity of the technology, the reliance on rare materials, and the realities of specialized manufacturing. In a peer conflict scenario, where hundreds of incoming missiles and drones could arrive in a single day, current inventories would be rapidly depleted. Defense economists point out that even if every missile produced in a year was sent directly to the front, the supply would still lag behind the pace of consumption seen in recent high-intensity conflicts. The gap between what can be built and what might be needed is no longer theoretical. It is a structural fact, visible in every factory schedule and inventory ledger. Inside the production lines that feed missile defense systems, the pace is set not by demand, but by bottlenecks that resist quick fixes. Each Patriot PAC-3 interceptor depends on rare earth magnets and guidance modules from single-source suppliers. When demand jumps, lead times stretch from months to over a year. The THAAD system faces similar constraints, with composite motor casings and navigation units produced by only a handful of manufacturers. Shipyards upgrading Aegis ballistic missile defense vessels can retrofit just 2 ships per year, limited by dry dock availability and the complexity of vertical launch system integration. Skilled labor is another ceiling. It takes years to train the engineers and technicians who assemble guidance seekers and propulsion units. Even with new contracts and funding, these workforce gaps persist. The result is a supply chain where surge plans often slip into multi-year timelines, leaving magazine depth and inventory replenishment capped by what the industrial base can realistically deliver. Today, every Patriot PAC-3 or THAAD system faces not just incoming threats, but the realities of industrial scale and economic asymmetry. As drone swarm warfare and hypersonic glide vehicles multiply, the magazine depth problem persists. Missile defense was designed for precision. Modern warfare is testing it with volume.